Hello, I'm Shawn Hargreaves. I lead the Direct 3D team at Microsoft, and I'm here to talk about mesh shaders. So really the whole purpose of this talk is to explain what a mesh shader is. I've tried to condense a really quick summary into this very first slide. So mesh shaders are part of the DirectX 12 Ultimate, which we're also referring to as feature level 12.2. They're going to be supported across different PC hardware and also on the Xbox Series X. What they are is basically a compute shader that can rasterize geometry, so they can submit a small index triangle list to the rasterization pipeline for pixel shading. This replaces all of the current geometry stages, so the input assembler, the vertex shader, the geometry shader, the domain shader, and the hull shader are all subsumed into this new mesh shader functionality. And this is a really important step in the kind of bigger evolution of GPUs. Over time, GPUs have been trending away from fixed function hardware towards more programmable compute-based approaches, and mesh shaders really move geometry into this new universe. So why do we want to? So this is really the future of the geometry pipeline. We think over time, more and more things are going to use mesh shader. Why do we want to replace the vertex pipeline? Vertex shaders have been around for a long time. They were introduced way back in 2000, which makes me feel super old because I was already in the industry when they were first introduced. At this point, vertex shaders are old enough to drink in the state of Washington. This is the traditional diagram of the vertex pipeline that I'm sure everyone's very familiar with. And it's actually pretty good. We're not replacing this because of a ton of problems. Vertex shaders have been a super effective programming model. One of the massive successes of vertex shader is that it expressed a very simple concept of a little function that has no side effects that shades just one vertex in isolation. But this enabled hardware to implement things in a massively parallel way, kind of behind the scenes. And because it hid the parallel nature of the hardware, vertex shaders allowed tremendous innovation in how hardware actually supports this. So the industry has run with this and innovated, and GPUs have got more and more capable, and it's been pretty great. But there are a couple of problems with this model. One is that the input layout is pretty inflexible. A vertex shader takes in index buffers and vertex buffers, which then get fed into the input assembler. So there's just things you can't do. Like, what if you wanted multiple sets of indices for different parts of your vertex data? What if you want to compress the data in some novel way? The input assembler is fixed function. It doesn't support that kind of operation, so you just can't do that. And in DirectX 10, we removed hardware support for triangle fans. You can't re-implement that in code. It's just not there in the input assembler anymore. The other interesting thing about this pipeline is culling can't really happen until the very end. I put a little asterisk saying that culling happens after vertex shading because there are some novel implementations that manage to cleverly do pieces of culling earlier. But basically, you have to finish shading a vertex before you can cull it. And that's kind of inefficient because you maybe do quite a bit of work before realizing that, you know what, this triangle is not even on the screen. The thing about vertex shaders is the model is conceptually very simple, but it doesn't actually really match the hardware. If we talk about what a GPU actually is, over the years they've converged to all work in basically the same way. A GPU is a set of SIMD processor cores, usually quite a lot of them. And each core runs some number of threads in SIMD lockstep. And then on each core there's a small amount of super fast local memory that can do things like exchanging information between the different threads, using operations like wave intrinsics in your shader. And that's exactly what a compute shader is. A compute shader is the closest thing we have in the API to expose what the silicon really is, like how does it work. Meanwhile, the vertex pipeline has been continuing to evolve a long time, since 2000. We've added hull shaders and domain shaders for doing tessellation. We've added the geometry shader. None of this looks like a SIMD hardware unit at all. It's a set of very linear stages where data flows through a pipeline. And the thing that all of these stages have in common is they all just run on a single thread. In the vertex shader, you program a single thing that operates on one vertex. The hull shader runs more or less, ignoring some details, once per control point. The domain shader runs once per tessellated point. The geometry shader runs once per primitive. At no point does the developer see that, in reality, this is a SIMD hardware unit. And that has some interesting implications. One is that the tessellator block in all of the middle of this needs to massively increase the number of threads. Because obviously if you tessellate a patch or some other curved surface, you're going to get way more points out that need shading than went in. And then geometry shaders really don't map terribly well to this at all. There are some interesting perf challenges and cliffs when you use geometry shaders. Because the model is you're running once per primitive, but at some point the hardware has to kind of pivot. It's been doing things per vertex, and then it has to shift to running per primitive. It's very hard for implementations to pack that and get awesome utilization. So Mesh Shader simplifies all of that way down. This is the diagram. There's only 3 boxes. The data is up to you. It's just data in memory. It goes into a mesh shader. That mesh shader is a compute thread group. It has access to all of the things that you expect to come along with compute shaders, like group shared memory and wave intrinsic instructions. And it outputs some triangles which go into the rasterizer. There's no association in this model between threads and vertices or threads and primitives. It's just a set of threads. It's up to the developer how they work. With Mesh Shader, for the first time, you're programming on the basis of a thread group of many threads working in cooperation, not just individual threads doing locally isolated things. And when it's done, the Mesh Shader outputs a little index triangle list. So this is one of these things that comes along pretty rarely in the evolution of programming models. It's a simpler diagram than what I had before, but it can actually do way more stuff, and that's why we're excited about this new feature. So this is a technical talk. Let's look at some code. This is a simple mesh shader. It actually works. It draws a cube. One thing I would call out, do not copy this code, whatever you do. This is a terrible, terrible mesh shader. And the reason for that is that I'm only using 1 thread. The whole point of GPU SIMD programming models is to run 32, 64, maybe even more threads in a thread group at the same time. If I run 1, I'm using guaranteed less, at best case, I'm using 1/32 of the capability of the hardware. So this is like crazy inefficient. Don't copy this model. But for learning how the model works, it simplifies some things to not have more than 1 thread. So this is a shader function. Its outputs are 2 arrays of vertices and indices, which in combination make up the index triangle mesh. I'm saying I have 8 vertices because it's a cube, has 8 corners, and 12 indices because a cube has 6 sides, but each side is a quad, so I'm going to make that up out of 2 triangles for a total of 12. These are the worst case sizes that my mesh shader could output. It's possible that once it starts running, it might decide it actually has less to output than it had pre-declared. So the next thing the mesh shader code does is calls this intrinsic set mesh output counts. And that's where I specify how many I'm actually going to write out for this particular mesh shader. In this case, the numbers are the same because it's always a cube. I'm not doing anything fancy here. And now I proceed to just write out my vertices. I'm specifying the positions and the colors for each vertex. This is kind of dumb and simple and not very flexible, but it's also a totally novel thing that you couldn't do before. I'm making up a cube out of thin air. There is no input data to this mesh shader. It's just code that runs on the GPU and it just creates a cube. You could not do this with vertex shaders or geometry shaders. You would have to feed in something. Like with a geometry shader, you could feed in a point and have it turn that into a cube, but you couldn't just create things out of nothing in code. And then finally, I write out the indices as well, and that's my cube. So this is a working mesh shader. This will actually run today on real hardware, but it's a super dumb way of doing it. So let's say we want to draw our cubes slightly more efficiently. What I'm going to do here is actually use more than 1 thread at the same time. And to achieve that, I'm going to move my data out. So instead of just writing all the vertices in code, I'm going to move the positions of the vertices for the cube into an array. And now I'm going to say I want 12 threads. The reason I picked 12 is I have 12 primitives to output, only 8 vertices, but 12 is like the most things I ever want to do in this shader. So I've said I want 12 threads. That's still not awesome. Like 12 is better than 1. I'm still not up to 32 or 64 like I should be to actually pack a GPU with fully efficient work, but it's better. So we'll run with this for a minute. And now I also have a little if statement. So basically the model here is each thread is going to output 1 vertex. Because I said 12 threads, but I only have 8 vertices, I need to just do a conditional. So the last 4 threads skip this and don't bother writing out a vertex at all. And then right at the end, I output my indices as well. One thing to notice here, I'm writing each index value from the same thread that corresponds to the index of that vertex. I don't have to do this. I could have a thing where I could say, okay, thread 0 is going to write index 15, and thread 1 is going to write index 10, or I could mix these up any way I wanted to. That will work. On some hardware, that will be less efficient than if I keep it 1-to-1. So the best model for best performance is always have like thread 0 writes vertex 0, thread 1 writes vertex 1, and the same for the indices. So that's a better cube. The thing about cubes is they're not terribly interesting unless you're implementing Minecraft. Generally, we probably want to draw like models with other stuff going on, right? So what might that look like? And now we have to start talking about some limitations. I can't just keep increasing the number of threads forever. There are limits on this capability. And these are the limits. I can have a maximum of 128 threads in a mesh shader thread group. I can write a maximum of 256 vertices and 256 primitives. And the total output vertex data size, more or less, again, I'm going to skip some details here. There are some alignment rules that you can find in the full spec, but these rarely apply. So it's safe to think about it that your output total size has to be fit in 32 kilobytes. And that covers all of the positions, the indices, any texture coordinates, colors, normals, other things that you want to output from this shader. So that gives us a bit of a problem, because most real models don't fit into 256 vertices. To solve this, we need to introduce a new concept called meshlets. A meshlet is basically just a piece of a big mesh. You take however much geometry you have and you split it up into little chunks, and each chunk forms a meshlet. This image I have here is a high detail model that's been split into meshlets, and then each meshlet was just moved a little bit so you can see the gaps between them. You dice it up into chunks that each thread group can render separately. The process of splitting this up, it actually matters quite a lot which triangles you put into each meshlet. If you just take them in order, you potentially get meshlets that are not very efficient. You want to share as many vertices as you can within each of these little triangle meshes. So this is a really similar problem to what you're very familiar with from vertex cache optimization in the old pipeline. We're basically taking what the input assembler used to do in real time while it was rendering graphics, and we're moving this to the asset bake time instead inside your pipeline. We're publishing a sample that shows how to do this meshlet split algorithm. There's a URL to it here. You can find some code there that you can download, learn from it, copy it into your engines, whatever you want to do. You could do this at load time as well, but please don't. The preference we have is that building meshlets should be done while your assets are baking as a compile step, and then the thing you ship on disk is the optimized meshlets already split up. If your engine wants to run also on legacy hardware that doesn't support mesh shaders, it's much better to ship meshlets, and then if the GPU can't render them at load time, just turn them back into index buffers. That's going to be way, way faster than going the other way around and shipping index buffers and then building meshlets on the fly. When you're transforming a mesh into meshlets in this way, your vertex data doesn't need to change at all. You can use the same vertex data you previously had. But your index buffer gets turned into 3 new forms of data: a list of meshlets, a list of vertex indices, and a list of primitive indices. And I have a little diagram here to explain what those actually look like. So here we have one meshlet. This one contains just 2 triangles. And so it says it has 2 primitives and 4 vertices to make up those 2 triangles. They're going to share an edge. So it's like dot, 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 making up a quad. That meshlet points into a separate array which holds primitive indices. And so the offset says where in this larger array to find the indices for this particular meshlet. And each of these primitives has a set of 3 indices making up a triangle. And then these primitive indices point into another array which holds vertex indices. And the reason that we do this is so that we can capture when 2 triangles share a single vertex. So that the first of the triangles, where its primitive indices are 0, 1, and 2, will point to these vertex indices. And my second triangle, 0, 2, and 3, points to a different set of vertex indices. The indices in the primitive indices value are relative to the vertex offset value that's specified in the parent meshlet. And because we've done this level of indirection, we can now say that even though we have 2 triangles, each with 3 vertices, would have made 6 vertices to shade, we know that we actually only have 4 unique vertices that are referenced by this thing. So we can also just go straight from that vertex count and vertex offset to the vertex indices and get just 4 of them. And then finally we have our vertex buffer, which is the same thing we would have used if we were drawing with conventional vertex pipeline, not using mesh shader at all. And those vertex indices just point to where to go and find the actual position, normal, texture coordinate data for that vertex. One thing I should stress here is this is not the only way to have geometry data for meshlets or for mesh shader. Mesh shader is infinitely flexible. You can have any memory layout you like. It's just code where you go and fetch the data. This is a sensible pattern that we think a lot of engines will find useful. It's a good data structure that's efficient to render, but it's not the only one. Knock yourself out coming up with creative other ways to pack models and compress things. So now I've introduced that concept, I can show you what the code to draw a mesh shader using meshlets would be. So this is replacing my cube shader with something that reads its geometry data from memory so it can draw any model at all. And so here we have the definition of the meshlet structure. That's exactly the same as I showed on the previous slide. We have a bunch of structured buffers for reading the meshlets, the vertex data, the indices, the primitive indices. And now we can go up to the full and say, okay, our mesh shader has 128 threads, which is the maximum size of meshlet processing we can have. A pattern you'll see very often with mesh shaders that draw more complicated things is they want to take in both group ID and group thread ID as parameters. The group ID basically tells the shader which meshlet is currently being rendered. That's which thread group is running. And then the group thread ID is an index to within that group. So it's saying which vertex or which primitive within the meshlet it's supposed to shade. And a really common pattern for mesh shaders in general is they often operate in different phases. I talked earlier about how there's no fixed association between a thread and what work that thread does. So what this shader is doing here, the highlighted section of the code is running on a per vertex phase. So each thread is doing math on a separate vertex. And then it switches, and over here each thread is operating on a separate primitive. And you can switch back and forth at different points in a mesh shader. There's tons of flexibility to divvy this up. You might do things if you were drawing a particle system, you might start out with each thread is doing physics for a different particle. And then at some point partway through, you would cull particles that went off the screen and then shift and say, okay, now each thread is doing per primitive work for the set of particles that are actually visible. So one of the goals of Mesh Shader is that we can hoist all of the previous pipeline on top of it. It's a superset of capabilities and can do everything that you previously could have. So basically anything that you previously did in a vertex shader, you can do in a mesh shader. Same for a geometry shader. Mesh Shader can do all of the kind of things of amplifying geometry, culling geometry, removing triangles, turning things into more geometry than came in. It's quite a bit more flexible than a geometry shader and usually will perform better, but it's a strict superset. One thing that's not a superset is streamout is not supported with Mesh Shader. You'll have to replace any use of streamout with just going ahead and writing to a UAV yourself in shader code. But if you're paying attention, you've probably realized hull shader and domain shader don't map directly to this model. So they need to start with a small number of threads and then expand into a much, much larger number of threads. So to replace that capability, we have a new optional shader stage that goes along with Mesh Shader called Amplification Shader. You can use a Mesh Shader on its own, or you can use an Amplification Shader plus a Mesh Shader. Amplification Shader is similar to Mesh Shader. It's a compute thread group that runs cooperatively over a set of threads working together. Does some math, whatever math you want to do, compute some things. And then it basically makes two decisions. It generates a payload structure, which can be up to 16 kilobytes of whatever data you want. And it decides how many Mesh Shader thread groups does it need. And then it launches them. So the key here is that the Amplification Shader has some number of thread groups. The Mesh Shader has some different number of thread groups, which could be less than the Amplification Shader or much, much more. It's up to you. And one of the obvious uses for this is culling. Martin Fuller's talk, which is going to come immediately after this one, will go into much more detail and show some demos of using the Amplification Shader for culling, where it will basically look at the geometry and decide, don't bother launching Mesh Shaders if the thing's not visible. And we'll have some performance figures on how useful that technique can be. So this code shows a very simple amplification shader, just to give you an idea of what they look like. Like my previous Mesh Shader example, it comes with a big caveat. Do not copy this directly. It's only using one thread, which is terrible, terrible. Never ship code like this, but it's good for learning. The key thing here is the amplification shader fills in a payload struct, and then it calls this new intrinsic DispatchMesh, passing in how many threads it wants in X, Y, and Z dimensions, and the payload. And that's what will launch the actual Mesh Shader. This is a cooperative call across the whole thread group. So you can't do this under divergent flow control. You don't get to have each thread of the amplification shader launch a different payload. There's only one payload struct, and all of the amplification shader threads are working together to decide what that should be. And then when the Mesh Shader starts up, it takes in that payload struct as data, and it can proceed to work just as before. So now we've talked about how to render geometry using Mesh Shader, we should talk about instancing. This is one place where getting really good performance needs a little bit of extra work. If you do the kind of naive thing, you would just scale up how many meshlets you need for your model with how many copies of the model you're going to instance, and that's how many thread groups you need. And then in the shader, you can do some math to turn the group ID back into a meshlet index and an instance index. Now, this is going to be great if your model subdivides exactly into a number of meshlets. Let's say you're building meshlets with 32 triangles in each. If your model is a multiple of 32 triangles, awesome, this is going to work great. If not, Let's just think about the math a bit. Let's say you had a mesh that contains just a single triangle. That's a really extreme case, but it does come up if you're drawing foliage or leaves or grass or something. In that case, for every single instance, you're going to be launching a whole thread group of 32 threads, but only using one of them. And that's terrible, terrible utilization. It's going to be like 3.3 and a bit% while you're shading primitives, wasting a ton of the GPU. If your mesh is 32 triangles, your utilization's great, 100%. If you go up to just 33 triangles, you go over a cliff, because now you have one thread group that's super efficient and shades 32 triangles. And then you have to launch a second one that only has one triangle left to shade, and that second wave is going to be very, very poorly packed. So as you change the number of total triangles in your mesh, you see this kind of sawtooth pattern where every time you go past a set of 32, the efficiency drops way off and then it builds back up. Not awesome. So how do you fix that? One solution is just ignore it and pretend it doesn't matter. If your model is big, that's actually fine. If you have a very large model that will occupy many meshlets and all but one of them are fully packed, it just really doesn't matter. It's lost in the noise if the last meshlet was only partially full. A probably better solution, which we expect most developers are going to want to follow, is to use packing. The idea here is to fill all the meshlets that are filled and dispatch those normally, and then dispatch this kind of special meshlet at the end, which will do some additional indexing, additional math in the shader to decide, and it can actually draw triangles from multiple instances at the same time. That makes things a bit more complex, but it will greatly increase your wave utilization. So if you're drawing small instances, strongly recommend you look into this kind of technique. Another experimental idea, which we haven't really proven out yet, but we think will work well. In a lot of engines, the lower detail versions of meshes are actually generated algorithmically by some kind of asset reduce. If you teach that algorithm about meshlet sizes, it can actually just completely avoid that problem by knowing that 32, 64, 128 are going to be efficient. Just try not to generate things that won't pack well. One final feature I want to talk about before I get onto what the actual API looks like. A new feature that comes along with Mesh Shader is the ability to output attributes per primitive rather than per vertex. We've always kind of had the idea of per primitive attributes in Direct3D. This covers things like the render target array index, the viewport index, which really only makes sense applied to a primitive. And you can also specify your arbitrary own attributes as being no interpolate, which means they get flat shaded across the whole primitive instead of interpolated between the vertices. The problem is there was no way previously in the API to actually write things per primitive. So instead we had this concept called a provoking vertex that basically took the data from a specific vertex. And I'm not going to go into details about that, but it had a lot of weird corner cases and there were some things it just couldn't do. So Mesh Shader fixes this. You can optionally, as well as outputting vertex data, we have a new out primitives keyword, which allows you to output a set of values that apply to a primitive directly. So this can cover custom values, things like render target array index, anything that previously would have been no interpolate. There's also a new intrinsic that you can write, a new attribute, sorry, that you can write from this, SV col primitive. And writing false to this indicates, writing 1 to this will indicate just discard the primitive. Don't submit it to rasterization at all. That can be super handy if you're trying to remove some triangles from within your mesh shader. If you didn't use this, you could just not write out the triangle. But the problem with that is you get a whole bunch of holes through your list of primitives. If you just decide I'm going to output 0, 1, and 2, skip 3, output 4, now you have to move 4 back to fill that hole. And you'd have to do a whole bunch of shuffling data across different thread waves. It's probably easier just output col for the ones you don't want and let the system handle that shuffling for you. So what does the API look like? We're developers here, we want to write some code. This slide's rather trivial. You should check for support. You do this by looking for the D3D12 option 7 and look for the Mesh Shader tier enum. That will tell you whether the GPU you're running on supports Mesh Shader. You need to compile your shaders. This will require getting a version of the shader compiler DXC from a recent version of the Insider Preview SDK, which includes the Mesh Shader support. And then you'll compile for 2 new shader models, MS65 and AS65. Which stands for, obviously, Mesh Shader and Amplification Shader, respectively. Loading the shaders uses a newish mechanism that many of you are probably not aware with. This has actually been in D3D for a while, but it hasn't been that widely used until recently. So you don't have to use this, but it's strongly recommended. Grab a copy of the D3D X12 header from this GitHub repository. This provides a bunch of helper structs that will make creating your shaders much, much simpler. And then the way this works, you define your own structure. This is a custom type defined in your game code, which contains just the pieces of pipeline state that you want to specify. And the reason we shifted to this model, previously we had a big struct that had all of the things that might ever be in a pipeline state, and you had to set every field in it. As things grow, that gets less and less scalable. Like if you're using Mesh Shader, you probably don't want to keep filling in, I don't have a whole shader, I don't have a domain shader. These things just don't apply. So in this model, you fill in members of this stream struct to contain only the pieces of data that you care about. So in this example, I've said I want to configure the sample desk, I want to configure an amplification shader and a mesh shader, and I've just left out the pipeline state fields that weren't relevant to me. Then I go and fill in those structs with the actual data, point them to the bytecode for my compiled shader, and then I use this create pipeline state API to go ahead and create the pipeline state. Once I've done all of that, I can now actually call DispatchMesh, which is the way I launch a mesh shader. This is a peer that sits along the existing draw API. Today in D3D we have draw, we have dispatch, which dispatches a compute shader, and we have dispatch raise, which launches ray tracing. So DispatchMesh is a peer of those for mesh shader. You pass in the thread group count that you want, and this will either, if you don't have an amplification shader bound, it will just launch the mesh shader directly. If you do have an amplification shader bound, it will launch the amplification shader, which then decides how many mesh shaders it wants and proceeds to launch those. And execute indirect also has the support you would expect. So you can compute mesh shader dispatches on the GPU timeline and use this indirect argument type dispatch mesh to invoke those. Our Pix graphics debugger is going to have full support for mesh shader. This is coming in the next release, which is due out anytime now. Depending on when you're viewing this talk, it might be out already. And I'm going to wrap up with a few links for getting started. So the mesh shader spec is available on this GitHub repository. That's the full engineering spec with all of the details of how the feature is designed and implemented. More detail than you would ever want in there. We have the sample I talked about earlier on GitHub, which shows how to build a meshlet. That consists of a little piece of library code that does the algorithm of splitting geometry up into meshlets. Then there's a command line tool that uses that, and a sample that just shows it in action, actually drawing some meshlets. To get operating system support for this feature, you need to install the Windows 10 Insider Preview for the 20H1 release of Windows. And you will need to use the matching SDK that comes with that Insider Preview to get access to the headers and libs and the shader compiler DXC that supports mesh shaders. I have the link to download Pix here. That support is coming soon. And for hardware support, this is available on any GeForce 20 series driver, 450.56 and above. So make sure you have the latest driver. And if you want to get in touch with the team, if you have any questions or feedback, this Discord link will show you how to do that. Finally, I'd like to share some thanks to people who provided content that was used in this talk. Matt Hurleman, Claire Andrews, Sarah Jabalia, and Jeff Noyle all contributed a lot to this talk, so thank you all for your help putting this together. I'm going to hand over now to Martin Fuller, who's going to show some mesh shaders in action and show some performance figures and more advanced techniques of using this capability. Thank you.